In order to think about how fast corrosion processes are likely to go, we must first consider what controls the kinetics of electrochemical reactions. The key thing that we're going to think about is what's going on at the interface between the metal and the solution that the metal is placed in. So we have a diagram down here, and we're zoomed right in such that we're just looking at a region which is a few molecules, a few atomic dimensions in thickness next to the metal surface. We have some water molecules in our solution, so we have the oxygen ion shown in blue and the hydrogen ions shown in red. A key thing about water molecules is that they are polar, that is to say that there is a charge separation and a dipole exists across the molecule. Another important point is that the surface of a metal will have some net charge. This is associated with the fact that the atoms that are actually at the surface won't be bonded to the same number of other atoms as will be the case for atoms which are in the bulk of the material. Sometimes the net charge on the metal will be positive, sometimes it will be negative. For this example, let's consider what would happen if the metal surface carries a net negative charge. Well, of course, these polar water molecules, at least the ones near the surface, will adopt a preferential orientation. The ones significantly far out will be randomly oriented, but these ones right by the surface, if the surface has a net negative charge, will have the positive side of the molecule oriented preferentially towards the surface. What that forms is a charge-separated region very close to the surface of the metal. That is to say, within the solution, there is a part very, very close to the metal, which is net positive, and then moving away a little bit, there's a region which is net negative. We call this region an electrical double layer, a region of separated negative and positive charge very close to the surface of the metal. Of course, if our metal happened to have a net positive charge, then the other side of the molecule would be preferentially oriented towards the metal, but it would still be the case that there'd be separated regions of positive and negative charges. The reason that this double layer is important is because once the electrochemical processes are happening, let's imagine I have my metal and it is corroding away to positive metal ions, then those metal ions, in order to get out and be dissolved in the free solution, must cross over this electrical double layer. That's going to cause there to be an energy barrier. If these positive ions are forced to move through a region which has a net positive charge, it will in general be more difficult for those metal ions to do so. Let's look at an example of that. Let's think about having a piece of metal, zinc, in a solution, and we'll set it up so that it's in a solution of its ions and it's in equilibrium with those zinc plus ions in the solution. What I'm plotting out down here in this diagram is a sketch of the free energy profile at the metal and then out into the electrolyte, the solution. And this is zoomed in close in this region of the electrical double layer. What I'm plotting down here is the profile of the free energy near the metal in the electrolyte, very close in the region of this double layer. So if the zinc and the zinc 2 plus ions are in equilibrium, then by definition they have the same value of the Gibbs free energy. So I'll have atomic zinc at this level of free energy and then ionic zinc 2 plus at the same level. We've drawn in on this profile an energy barrier across the double layer. That is to say, in illustration, that there will be a region where it will be more difficult for the ions to cross over. Our processes are going to be either zinc going to zinc 2 plus 2 electrons happening from left to right, or zinc 2 plus 2 electrons going to zinc happening from right to left. But whichever way that happens, it involves the zinc crossing over this charge-separated region. Of course, if this process is at equilibrium as we've defined it, then both of these processes will be going on, but they'll be happening at the same rate. The rate at which ions can cross from each side to the other will be equal.